Good morning, everybody. Thanks for your patience. We'll get started here in about 10 minutes or so. I apologize. I had an unexpected meeting that I had to attend at 10 this morning, but I cut it short. So we'll get started here in just a few. Thanks for your patience. We'll get started in about 5 minutes. Thanks for your patience. We'll get started in just a few minutes. Thanks for your patience. We'll get started in about 2 minutes. Thanks for your patience. All right, thanks everybody for joining in this morning. Again, my apologies for having to start us a little bit late today. I had a 10 o'clock meeting. So I teach for Nunez part-time as an adjunct, but I have a full-time position at River Parishes, and my vice chancellor called a meeting for us at 10 o'clock this morning. So that was kind of out of the norm or unexpected, but you know, when the boss calls, you got to be there. So I was fortunate that the meeting ended at 10:30, ended early, and I was able to get here for 10:30. So thanks for your patience on that. Hopefully I won't be having to deal with that kind of situation in the future, but we'll do the best we can, right? Okay, so I'm going to go ahead and share my screen. Somebody please kindly unmute and let me know if you're seeing the course homepage.
Yes.
Yes.
Okay, thank you very much. So let me just jump right into the weekly overviews. So remember, the weekly overviews are your breakdown of what we're doing, the activities that you have to complete, and the resources to help you get that done, right? So on Tuesday, we took a look at science in general. We focused on the scientific method, looked at an example utilizing the steps of the scientific method. We also talked quite a bit about the connection between science and technology. And then we moved into looking at measurement. In particular, we focused on the base properties and base units in the metric system. And then we looked at the metric prefixes and their associated powers of 10. And so what I want to do today is to pick up there and begin to look at what we call derived properties, okay? And so to do that, I'm going to utilize my extra resources that I made available to you. Now, you might be wondering, well, why not just put them in the weekly overviews? Well, there's some stuff that behind the scenes that, you know, I don't want to get into as to why I don't put these in the weekly overviews, but you have access to them right through the announcements. You just click on that extra resources tab and notice what you have access to. There is a folder for every topic that we cover. So I'm going to go into the measurements topic, and you can see that there's some pretty good stuff there for you. Okay, the nature of science. Next week when we get into measurement unit conversions, and then I'm going to go into this one because I like the way they talk about derived units. Okay, but let me just kind of refresh you, right? So, you know, I highlighted on Tuesday the notion of units, right? That the whole idea is that in physical science, the knowledge that we, you know, have packaged, if you will, is based on our observation and measurement, right? And measurement is one of those key aspects of an experiment because that's part of that whole data and analysis and results and conclusion piece, right? And it's very important that you understand right from the start that units matter. In fact, if you are measuring something and you put the wrong unit, then you have described that part of the physical environment incorrectly. Right? And so I always tell students, if you're doing working problems for me and your unit is wrong, it's wrong. Because one of the things I really stress heavily is the importance of measurement. And you can't measure without using units properly. Okay. And so here is another chart that focuses on the SI units. We focus heavily on the first four in this class: length, mass, time, and temperature. Those are the base properties, base quantities, base characteristics in our physical environment. And there you have the base units that go along with them and their abbreviations. So we focus on length, mass, time, and temperature in here. But as I told you on Tuesday, you know, if all we had to do was those four things, then this would be a straightforward and class that we could finish right now. But the idea is that we make combinations of those base quantities. And as a result, we have to make combinations of those units. Okay. And so here is, I guess you could say, a more condensed form of the prefix table. These are fairly representative of the ones that we'll use more consistently in this course. Again, I don't need you memorizing them, but I need you to understand that when you use prefixes, what you're doing is utilizing the associated power of 10, but in a more communication friendly mode, right? I don't have to keep writing all those zeros, if you will, when I'm dealing with fractions of our base or multiples of our base. All right, so the whole prefixes and powers of 10 is meant to facilitate consistent communication, right? So we've standardized our measurements by working with the metric system, and we refine our communications even more by using these consistent prefixes and powers of 10. All right. And so now what we want to do is we want to move into looking at this notion of derived properties and derived units. Okay. And we'll focus on two of these derived properties, volume and density. Now, those of you who have me for lab, you know that these are this volume property is one that you are utilizing to do your first experiment. Okay. And so the way we get this derived property volume is by combining length times length times length. Remember, length is a base property. And so we're making combinations of our base property. We're saying take the base property length times the base property length times the base property length. And when you multiply it that way, you get a new derived property called volume. So the way you get a derived property is to make combinations of your base properties. And then you'll see here in a minute, you can even make, combinations of bases and derived properties. We'll talk about that in a moment. Okay. So when a lot of times in a math class, you might hear length times width times height. But when you dig deeper, width is a length, so is height. So in essence, what you're doing at a fundamental level is length times length times length. And that gives you a length volume in cubic length units. An example of a length unit is centimeters. But if I take centimeters times centimeters times centimeters, I have centimeters cubed. If I take inches times inches times inches, I have inches cubed. Miles times miles times miles, miles cubed. So if I take any length unit and multiply it times itself 3 times, I get a cubic length unit, which represents volume. Okay. Now, most of you, when you think of volume, probably think of liquid units like fluid ounces and gallons and pints and quarts, cups, milliliters, liters, So there's an equivalence between a length volume, cubic units, and liquid volume. And you see they're given 1 centimeter cubed equal 1 milliliter. Those of you in lab, remember that when I talked about the lab report, that was a key aspect of your volume analysis, because that let everybody know how you transition from the cubic length units that you measured to the liquid units that are actually on the label. Okay. And then they give you another example of a conversion. 1 decimeter cubed is equal to 1 liter. So there's an equivalence between length volume units and liquid volume units. So that derived property volume is found by taking length times length times length, and then you can equate that to liquid volume units. Okay. Any questions on that derived property volume?
No, ma'am.
Okay. Let me ask somebody a question and see if you got your thinking caps on. If I said I make the combination length times length, what property is that? Anybody want to take a stab at it? If I just did length times length, what property would I be dealing with? So if I said I had square inches, somebody tell me if you're thinking, what property goes along with square inches? Like if you're going to put carpet in your house and you measure it and you got square inches. Anybody?
Height.
Not height. Height would just be inches, right? But I said I had square inches, inches times inches.
What?
Area, right? So you see, if we took a length times a length, or inches times inches, for example, that's area, right? That's the property area. That's a derived property, right? So, and you'll see that whole idea of a area if you continue in this and you look at the property pressure. Pressure is a property and is force per unit area. So you see those square inches, you know, you might have heard the unit PSI, right? Pounds per square inch. So you see they're using a derived property area in that situation. And that the way you get an area is you take a length times a length. So square inches, square feet, square miles, anything square, and you're dealing with the property. Well, let me say anything with a length unit squared, and you're dealing with the derived property area, right? So you see, I always tell students, you've been doing this stuff and seeing this stuff all around you for your whole life. You go in a grocery store and pick up a can of corn, or pick up a 2 liter of soda, or, you know, cans of soda, baby formula. All of those things have units on them, which relates them to measurement, right? And you've been seeing this all your life, but, you know, I would tell students, don't throw away your experience. You know what these things mean. You just really never had to like nail it down for a purpose. Well, now you're using that experience that you have for a purpose, and that is to help us explain how our physical environment works, which is based on measurement. Okay. All right. So now let's look at another derived property, and that is density. Density is an example of a derived property. Remember, when we say derived, it means you get it by making combinations of other properties. Okay, so what properties do we need to make density? That is mass per unit volume. Okay, mass per unit volume. So we take the base property mass. Remember, our 4 base properties are what? Length, mass, time, and temperature. So we take the base property mass and we divide it by the derived property volume. Okay, mass per unit volume. All right. So you see, you get, like I said, it's all the combinations that you have to make to help us understand our physical environment. Okay, that's, you know, where the that's what the challenge is, right? Is to understand this notion of making combinations to help you explain what's going on around you. All right. So this derived property density is critical because it helps us to identify substances, because every substance has its own density, right? And imagine if we're trying to explain things happening in our physical environment, we need to be able to identify and categorize those things, and density is one of the ways we do that. Okay, so gold doesn't have the same density as lead, okay, for example. And the way we measure this property is by measuring the mass per unit volume. Okay, so in the box you see on the screen there, I'm hoping you are seeing the screen I have up, right?
Yes, ma'am.
Okay, great. I was like, oh my goodness, I'm talking and they can't even see the screen. What? We're good. So in the square, you see the formula for density. Okay, the formula. When we say formula or equation, we're talking about the symbol notation. Okay. Now, if we want to talk about, what those symbols or variables stand for, D stands for density, M stands for mass, V stands for volume, right? And then in the triangle, I call it my problem solving pyramid. So let me stop the share for a moment and open up something that's going to clarify that for you. Let me open this screen right here. Okay. And now let me share that. Okay. So there's our 4 base properties and 4 base units. And here is what I call my problem solving pyramid. Okay. So on the right side, you see the formula for density. D equals M over V. Density equals mass per unit volume. But on the left side, I took that formula and I put it in my problem solving pyramid. And I will use this technique throughout the course to keep the math simple, right? So you don't, if you're using my pyramid, you don't have to understand equations at all. All you have to do is look at the pyramid, and any 2 variables that are right next to each other, they're being multiplied. So in this instance, D is being multiplied by V to give us M. If we're looking at variables that are one on top of the other, that means we're dividing. So in this instance, if I want V, I take M divided by D. So see, I reduced the need to understand equations. I like to say, I took the algebra out of it. And I put it in a format where all you have to do is multiply or divide. Okay. Does that make sense to you?
Yes, ma'am.
Yeah. And I will try as much as possible in this course to model the things that we have to do utilizing this problem solving pyramid. So if you know how to multiply and divide, you're pretty much set. Okay. All right. So let me stop the share and then go back into my other screen. There we go. Do that. All right. So on the smiley faces, fill them in with the picture. For whatever reason, whenever I turn this into a PDF or whatever, it won't translate the variables very well. It replaced them with smiley faces, right? But we know that, that's M on the top and D and V on the bottom, because I showed you in the other picture. And I'll make that picture available when I post the recording for today. All right. So let's look at some examples that deal with this derived property density. Okay. So it says an object has a volume of 825 centimeters cubed and a density of 13.6 grams per centimeter cubed. Find its mass. Okay. So they gave us the volume and the density. They want us to find mass. So if we cover up the M, because that's what we're looking for in our problem solving pyramid, then we're multiplying D times V. So let's do that. 13.6 grams per centimeter cubed times 825 centimeters cubed. Okay. Our centimeters cubed cancel out because you can cancel like variables. And you have 11,220 grams. Okay. So this is the point where we start the problem solving. And just so we do things consistently, I always tell students, in your final answer, you can round off to 2 decimal places. That's sufficient, 2 decimal places. Okay. And I think I mentioned that in lab the other day as well, 2 decimal places. All right. Says a liquid has a, well, let me not jump so quick. Let me ask, are there any questions about this particular problem?
No, ma'am.
Thank you. A liquid has a density of 0.87 grams per milliliter. what volume is occupied by 25 grams of the liquid? So you see here, they gave us the density, they gave us the mass. And notice in the question, they did not tell us occupied by a mass of 25 grams. They just said occupied by 25 grams. The reason they can do that is because grams can only be mass. Grams can't be used for density. Grams can't be used for length. Grams can't be used for volume. If the unit is grams, the property is mass. Okay? So that's why it's important to know what units can be used for a particular property. So for example, if we're dealing with mass units, that's grams, that's ounces, kilograms, milligrams, megagrams. Just put a prefix on it, right? If we're dealing with density, you have to have a mass unit on top and a volume unit on the bottom. So grams for mass on top, milliliters for volume on the bottom. It could have been kilograms per liter or ounces per fluid ounce. As long as you have a mass unit on top and a volume unit on the bottom, that's a valid density unit. Okay. And so in this particular problem, because they want us to find volume, we have to cover that up in our pyramid and then do mass divided by density, M divided by D. So that's 25 grams divided by 0.87 grams per milliliter. We have like units there, grams on the top and grams on the bottom. So they cancel out. And you can use your handy dandy calculator to get the number. That's 28.7. And the unit that you have left is milliliters, which is appropriate, right? Because volume units, milliliters, kiloliters, liters, gallons, fluid ounces, pints, quarts, cups, all of those are valid volume units. But in this example, the unit that you should be getting is milliliters, okay? So you can see here the importance of getting the unit right. Because if I solve this problem, for example, and I had 28.7 grams, I'm not talking about volume. I can't use grams for volume. I can use grams for mass, but I have to use milliliters in this case if I'm accurately expressing a volume, okay? And that's what I tell students, when you're solving problems, check yourself. Is your number correct? Does your unit make sense? Okay. And then finally, the last example, you have a sample with a mass of 620 grams and a volume of 753 centimeters cubed. Find density. Well, they gave us the mass and they gave us the volume. So cover it up. I want density. It says I have to do what? M over V. So that becomes 620 grams divided by 753 centimeters cubed. Hey, in this case, nothing cancels because I don't have any like units. So my answer has to be grams per centimeter cubed. And that's a valid density unit because it has a mass unit on the top and a volume unit on the bottom. Okay. So what I've done here is worked 3 examples for you. Each one of them finds one of the variables in the density formula. This example, you find M. This example, you find V. In this example, you find D. So when you are working through those sample problem, those problems that deal with density in your problem set number 1, you can come back and refer to this as a way of helping you to make sure you're approaching the problem correctly. So if the problem you're working on in your problem set asks you to find M, then you can come back and look at the example here where you find M to see, okay, how do I do that? Okay. Any questions on any of these problems that I've solved?
No, ma'am.
Cool. So also for your benefit, if you look under useful links, hopefully I'll come up here. Yeah, you see sample density problem. Okay, so you have access to some additional help here. And I do believe I put a link to that in the weekly overviews, if I'm not mistaken. Let's check and see. Sample density problems, same place, right? So I made sure in the readings and viewings, you have the items that you need. And discussion is what you have to complete by this Saturday. And, you know, some of you have even started working on a project. Kudos to you for sending me an article at this early stage in the game, because it means you're getting that off your plate. And of course, if you have questions, you can post in the class questions forum. Your classmates are free to respond to you there. If you need me, you can join me during office hours, or you can shoot me an email. You can call me, whatever you need to get your question answered. Okay. So that concludes my part of the nature of science. Now your work begins. Next week, we'll start dealing with measurement. I call it measurement 2. And that primarily focuses on unit conversions. All right. What are your questions? Well, that concludes our class meeting for today. I will post this recording by tomorrow, and I'll also share that that whiteboard that I put that I opened up for you here. And everybody have a great weekend.
I have a quick question.
Yeah.
Would you rather us ask questions about the discussion in our Zoom, or would you rather us post it to like the class discussion?
I would rather you do it whatever way is most convenient for you.
Okay, I'm kind of confused about the question about the mass of a flea.
Yes, ma'am. That's why it is just a basic question for you to see how well you can estimate. I want to know in your mind, what mass do you think would be attributed to a flea? You know, if you had to guess the mass of a flea, what do you think it would be?
Okay, that's what I was trying to get at. Thank you very much.
Yeah, it's you know, it's just to see what's going on in your head. I mean, you know, I've got students who put out there 1 kilogram, and I'm thinking that's the biggest flea in human history. You're right, because no way a flea has a mass of 1 kilogram. But see, it's designed to kind of force you to get inside these units and see what would be reasonable, right? I'm not asking you for the exact mass of a flea. I'm asking you in your mind, work through this whole unit business and estimate what you think it might be. That help?
Yes, ma'am. Thank you.
No
Do
problem.
we have lab today?
Yes, you have lab every Thursday.
Okay.
Any other questions? All right, so I will see those of you who are in lab with me at 11:30. Other than that, I really appreciate you joining in and participating and asking questions. Everybody have a great weekend.
Thank you.
Yeah,
Thank you too.
Thank you.